Here's what we got from last time. We have second order differential equation, constant coefficients, and then we use a quadratic formula, and then we came up with 3 possible scenarios. And then we handled each of those scenarios, and now we should know the solutions to them. And I was thinking about doing another second order just for practice, and then after that we're going to carry this on over to higher order differential equations. So let's do an example with a second order differential equation, and let's stick with here between 1 and 14. I don't know which one we did last time, but let's pick a number between 1 and 14. 6. Too late. Let's get started. Here we have our second order differential equation. If we do the appropriate substitutions with our guess of a function, then we factor things out. We get what's called the auxiliary equation. So let me jump to that already, since we did last time, and then we'll take a look at auxiliary equations again later. So our auxiliary equation will be m squared minus 10m plus 25 equals 0. It looks like this is 5, right? M minus 5 twice. So m is equal to positive 5 is a solution, and we might want to make a note this is multiplicity 2. So we know that we fall in the second category. You know, it's not distinct, it's not complex, it's the same thing. And so we know for sure that one of our solutions is going to be e to the 5x. And you can put that into the differential equation to double check. Now, without doing any more work, and because we know that the reduction of order will give us the solution, the second solution is going to be x e to the 5x. Okay? The reduction of order will confirm or will give us our second solution. We have one solution already. If we put e to the 5x again as our second solution, well, they're the exact same thing, so they're linearly dependent. We want 2 linearly independent solutions. And so the second solution is going to be x e to the 5x. And you can verify that by using the reduction of order process. Yeah?
So if multiplicity can we just add the first solution
x e to the mx. Yeah. On the test situation, yes, unless I specifically say use the reduction of order formula to get this. Okay? So I'll say it's free now. You are allowed to say, if it's repeating, your second solution is just x times e to the mx. If it's repeating for third order, then we'll take a look at it. We'll prove it once in class. You could use it unless I specifically say that you have to use reduction of order to find it. Okay? So we have 2 linearly independent solutions, y1 and y2. Our general solution can now be written as y equals c1 times y1, which is e to the 5x, plus c2 times y2, which is x times e to the 5x. And then if you had some initial conditions, you would throw them in to solve for C1 and C2. And then you would have the general solution to your IVP. Or not general, but the specific solution to your IVP. Okay? Well, we'll do some more examples. Maybe we'll run into a complex one. Maybe not. Let's get higher. Whoa. And let's try to approach it the same way we've been approaching this. And again, we'll see a pattern. We'll go from the differential equation to the auxiliary equation to the solutions to your polynomial, and then figure out what our solutions are from there. So let's find 15 or 16. Let's do 16 because it looks easier. It's probably all going to be hard, but let's try this one. So this is a 3 primes there. So the third derivative minus y is equal to 0. And let's find the general solution for this particular differential equation. So again, we'll start off by assuming that your solution looks like e to the mx. And then what we're going to do is we're going to find derivatives, plug it back into the original equation, and then see if we can find a simpler solution. Now we don't need y prime or double prime, but we do need it to get to y triple prime. So this is our third derivative, which is just another m pops up. And then when we plug that into the differential equation, we're going to get m cubed e to the mx minus e to the mx is equal to 0. And the same thing. And then you shouldn't be surprised that we're going to get a differential, we're going to get a simple polynomial that looks awfully like your original differential equation just by looking at the coefficients. All right. So auxiliary equation is m cubed minus 1 is equal to 0. So that's what we're solving for. We're looking for values of m that would make this work. Now, this is where you're going to have to dig into your Algebra 2 knowledge about factoring polynomials and try to factor them as much as you can. And if you remember two perfect cubes, the difference of cubes formula, then you're in good shape. If you don't, well, let me just remind you that it kind of looks something like this, unless I'm wrong. Which is quite possible. So I have a linear term, m minus 1. I can see the solution, m is equal to 1, will be popping out. And then now I have a quadratic that looks like it's an irreducible quadratic. I'm not going to be able to factor this if you try to factor it. If you're able to factor this, then you're wrong because you can't factor it. So unless you go into complex numbers. And that's what's going to happen is we're going to go complex here again. So let's take this and find your complex number solutions by the quadratic formula. So negative b plus or minus the square root of b squared minus 4ac over 2a, 2a, a is equal to 1. So we got root 3 in the, we got root negative 3 under square root, which is going to give us an imaginary number I. So we have negative 1/2 plus or minus the square root of 3 over 2i, if you work all that out. So you got the complex conjugate business again. Okay? So remember that for a third order differential equation, you're looking for 3 linearly independent fundamental solutions. And you got m is equal to 1, which gives you a solution of e to the 1 times x. As your first solution. Now, the 2 other solutions that came out of m, complex conjugates, would give you a pair of solutions. You remember what they were? E to the this power, right? Which ends up, by Euler's formula, it becomes cosine and sine. Okay, so let's make that a little bit more more clearer. Let's make it a little bit more show more steps. Let's make it. Let's show more steps. So our possible solution here is e to the negative 1/2 plus or minus root 3 over 2i, and I think the example that we had didn't have a real part. This one has a real part, e to the negative, oh, that's times x. So here it's e to the 1/2 x times e to the plus or minus root 3 over 2i times x. So this is the one that eventually breaks up to the sine and cosine. But I wanted to point out that this particular one has a real part in your solution, and so that e to the negative 1/2 x will be part of your solution. So let me just not do that and just actually write down that this is a combination of cosine root 3 over 2x and sine root 3 over 2x. So remember, the I belongs to the sine, but I is a constant, and so all that stuff will get merged to become constants anyways. So there is a bottom line here. The bottom line is that now you know the other 2 solutions that you're looking for. So the first solution is e to the x. The other 2 solutions will be e to the negative 1/2 x times cosine root 3 over 2x. And then the other one is e to the negative 1/2 x times sine root 3 over 2x. So these are your other 2 solutions. And then now, if you want to write this as one general solution, you just write the linear combination of all these functions. So we got the C1 times the first one, y1, which is e to the x. We have C2 times y2. And then we have the C3 times y3. Add them all up and get the general solution. Okay. So what do I want to see? I think what I really want to see you do is what I want to see me do is change pens. What I want to see you do is you start off with your differential equation, And you can, if it's obvious to you already, you can skip down here. If it's still unclear how you're getting the auxiliary equation, I suggest that you go through this process several more times until you get used to it. But really, the bottom line is that you'll get to this this auxiliary equation, and then you solve for that. You solve for your equation, and then you come out with your solutions. So how you solve for it, it's up to you. Sometimes it'll be easy, it'll be obvious, you can factor things out. Sometimes you might know one solution, then you might have to do synthetic or long division. It's a polynomial, so it should be something that you should try to remember. You did it some time ago, back in Algebra 2 or something. As you were doing it, you were probably saying, when am I ever going to use this? Now, you're going to use it now. Okay? Like, difference of 2 cubes. When am I ever going to use that? Oh, here we go. And then your general solution, of course, is your answer. Okay, questions? All right, why don't we try to pick another problem here? 16 through 19, pick one. Let's stay cubic for a little while. Pick one, 16 through 19. 18. So let's do number 18. Actually, why don't you try to do number 18 on your own? I'll give you about 2 or 3 minute head start. 18, you said, right? Somebody said. And then we'll do a 4th order differential equation after that. So go ahead and do this. Let's try to do this problem. Okay, I'm gonna jump directly to the auxiliary equation. That you can save some steps. So this is the 3rd power. I see that this is going to be m cubed plus 3m squared minus 4m minus 12 is equal to 0. So look at the relationship between the y's and its derivatives versus the m's and its powers. We can actually take a look at this as m to the 0 power times 12, or negative 12 times m to the 0 power. It's looking at the 0th derivative. M is to the 1st power. This is negative 4 times y to the 1st derivative. And so you can make that relationship that way. Factoring this, I would probably try to factor by grouping. I don't know. So when there's 4 terms, it's a 3rd order. When there's 4 terms, then I suggest you try to look for a hint where it might be factored by grouping. And again, it's one of those things in Algebra 2 where you would think, oh, when am I ever going to use that again? I found it useful. So I would group these two, and for the first two, I factor out an m squared. And then for the next two, I would factor out a negative 4. And my hope is that the stuff that's in parentheses will be exactly the same, so I can, quote, factor that out. And so it looks like I can factor out an m plus 3 from these two, and then I would have an m plus 3 factored out, or at least this is how I do it, m squared minus 4. And then m squared minus 4 is m plus and minus 2. And it doesn't matter which one you call m1, m2, m3, and which one you call y1, y2, y3. But I think for a lot of convenience sake, people tend to use a smaller number as m1 and the larger number as m higher than that. So if you solve for this, I think I get negative 3, negative 2, and positive 2. So it would go in that order. Okay. So that's done. Now I know my solutions. Now I'm practically done, right? So if you want to make a list of your fundamental solutions, sometimes that's what they ask for. Then you make a list. If you just want the final answer, then you could probably skip to the final answer, right? So I'll write down the fundamental solutions. E to the negative 3x. Don't forget the x, right? Because it's a function of x. Y2 is equal to e to the negative 2x, and y3 is equal to e to the positive 2x. And usually this is what they look for, the general solution. So you just want to write out the linear combination of those functions. Okay. All right, let's do a fourth order or higher order. I guess between 23 through 28. 28 is a fifth order. 27. 28 probably would have been easier. Oh, I don't know how to factor that. We could factor it, I suppose. All right, well, let's practice factoring then. That's what. All right, well, let's take a look. So we'll remind ourselves of some factoring tricks. So I'll give you a minute to try to factor this. I mean, after you write the auxiliary equation. What? Sure. Sounds like you need to sit in front, John. Or get yourself some new glasses.
Well, I suppose.
I need new glasses. With that stage now, I have to get progressive glasses because I can't see close up. Oh, mid pause. Let's try to do this. Start off with your auxiliary equation. M to the fifth plus 5, m to the fourth minus 2, m to the third minus 10, m squared plus m plus 5 equals 0. If you have any hints of what the solution might be, like what would make this equal to 0, like if you try putting 5 in there and you see 5 is equal to 0 or negative 5, then you could do long division. And if you don't remember that, I want you to just try to look it up. Long division or synthetic division, and that stuff is good for trying to solve for these polynomials, these long polynomials. What was that ever good for? When am I ever going to use long division for polynomials? Here we go. All right, so so it looks like if we pair them up, we get 3 pairs, and it looks like there's going to be a common theme running on throughout. That's m plus 5. So let's see if we can factor out an m, and we see if we can factor out something where we would have an m plus 5 in these 3 pairs. So let's factor out an m to the fourth, m plus 5. There we go. That's 1. Let's factor out a negative 2, m squared. And that will give you an m plus 5 again. And then the last one is just plain m plus 5. So now you gather all the m plus 5s and factor that out. And then what do you have left? You have an m to the 4th minus 2m squared plus 1. Well, so this is a perfect square. It will be m squared minus 1, it looks like, right? Squared. And so this will give you m minus 1 squared m plus 1 squared. So this is still an interesting problem. Beyond factoring the polynomial, it'll be an interesting problem to take a look at how we're going to negotiate the different solutions that we're getting. So let's take a look at the solutions that we're getting. We got m is equal to negative 5. Here we have m is equal to 1 with multiplicity 2. And then here we have m is equal to negative 1 with multiplicity 2. So the stuff with multiplicity 2, remember, we'll need some sort of, because this will only generate one linearly independent solution, we would technically go ahead and try to use the reduction of order to try to figure out what our second solution would be. But we know the answer already, so give us permission to not go through the reduction of order and just get the answer. So what are our answers? So we got y1, let's designate the first one as y1, e to the negative 5x. Let's do this y2, just to be consistent with the ordering. Again, it doesn't matter, but I'm going to order this as y2. y2 is equal to e to the negative x, negative 1 times x. Now, to get this, because this has multiplicity 2, to get the second multiplicity, I would need a second linearly independent solution. So I'll throw in an x, e to the negative x. Again, without showing the work, this is through the reduction of order. So now you have 3 solutions, and I got 2 more out of this one. So y3 is equal to e to the 1 times x, and then y4. Wait, that's sorry, this is y4, and then y5. I need 5 of them. Okay. So that's it. General solution. Y is equal to an arbitrary constant, and then y1. You know the rest. I'll write it out anyway. So e to negative x, c3x e to negative x, c4 e to the x, and c5. Yeah, whenever that happens, you have to treat it like this. So the repetition happens when you get multiplicity. That's the only time it'll happen, and when you do that, you just compensate by throwing in an extra x in there. And without doing the work, it comes from the reduction of order. Okay? Yes? Yeah. You just keep adding an x, or keep multiplying by an x. Do you hear a question? Which is Erica's question. From the beginning, if this has multiplicity higher than 2, then you just keep tacking on an extra x in there. Okay, so let's see. Are we done? Move on. just higher multiplicity. Let's just do that as an example. Yeah.
So if there are two, so each thing with the multiplicity, if there's like one thing with multiplicity 2, then that becomes basically whatever it was times x plus constant.
Times x.
Just because one of them gets an x and one of them doesn't get an x. So
Yeah, you can think about it that way. Yeah. Yeah. That's the reduction of order. That's how it comes up through the reduction of order.
So if there's a term with like multiplicity 3, then that would just become, that term alone will become like either negative x or whatever times x squared.
Yeah. Yeah. So let's take a look at the idea of multiplicities and see if I can come up with an example here. Let's go to the fifth power again. Let's see if I remember my what's that called? Pascal's triangle. Y. You know that if you see a number that's in parentheses, that's the derivative, right? Fifth derivative. Let's go 5 y to the fourth. And next one is, what's Pascal's triangle? Is it 10 or 15? I don't know. 1, 1, 2, 1, 1, 3, 3, 1. Maybe I should have just went to the fourth. 10. There's 2 10s. Anyways, Pascal's triangle helps us find the coefficients of the binomial theorem. So if I were to write this as in the auxiliary equation, I would get m to the fifth plus 5m to the fourth plus 10m to the third plus 10m squared plus 5m plus 1 is equal to 0. And this happens to factor out as plus 1 to the fifth power. Okay? So I have 1 or negative 1 of multiplicity 5. So if that's the case, then what are my functions? So my fundamental functions, we'll start off with the first one. And then through several reduction of orders, you'll see that it'll just be the original e to the negative x function where you keep tacking on an x. So y to the third, y sub 3 is x squared, e to the negative x. Y sub 4 is x the third, e to the negative x. And then the last one, and you can pull out any of these and double check to make sure it actually satisfies this differential equation. And it should. And then you can imagine just stringing them up to be your solution. Okay? Yes? Because that's what's going to happen if you do the reduction of order formula. And I suggest that you all try it. You guys just had a quiz on it. Oh, um, oh, you have to. We only do that for one, huh? Um, just do a linear combination of the first two that you already know, and then reduce it. Yeah, yeah, something like that. Um, there's one more multiplicity that we should probably cover, and that's the possibility that you're going to get something like this: y fourth order. Let me see if I remember my plus 2y double prime plus y. I think that'll work. I know what I'm trying to get at here. What's this equal to? Or the auxiliary equation? M to the fourth plus 2m squared plus 1 is equal to 0. Looks like I can factor this, right? It's a perfect square. M squared plus 1 squared. Is that correct? That's what I want. So here I have imaginary numbers of multiplicity. So m plus or minus I with multiplicity 2. So remember, when you have an imaginary number, your solutions, y1, would look like e to the 0. The real part is 0 here. And so we can just ignore e to the 0. And then you have cosine of the coefficient of I. So that's just 1 times x. Then y2 is equal to sine x. Right? So if this didn't have multiplicity 2, I would be done with my solutions. I would just be looking for 2 fundamental solutions, and then that would be it. But this has multiplicity 2, so what we would do is we would imagine tacking on an x to that e to the ix business that we would have. And what that would do is just really tack in an x as another coefficient of sine and cosine. So your y3 be x cosine x, and your y4 be x sine x. So you have these 4 linearly independent fundamental solutions to the differential equation, and then again you just string them all up with a constants in front. Okay? Any questions? Yeah, this is so cool. No? This is different from your other looks. This is like, oh, now I'm just bored. It's not the confused look anymore. It's just like, so it's either you're on this thing, you know it, and then you're so bored that I could do this in my sleep, or I'm so lost I don't even know what to ask. It's like the bimodal distribution from our exam, right? All kinds of people got A's, and then the other side. That's what that look is what I'm seeing. I did. No. Yeah. All right. We're going to push for the last 9 minutes or so to the next section. because it is. What section is this? This is 4.4. No. Does it say this Sunday? It might be this Sunday because I haven't adjusted it because we have that flex day. There's no class on Thursday, right? You know that? Yeah, I'm gonna miss you. So what we're doing here is you're trying to find solution to a more general differential equation. So we'll start off with an nth order differential equation again. Can I just copy from somewhere? I have to write it all out. Let's see, y. This is gonna take too long. In parentheses, see, this is gonna take too long. Oops, that's dot, dot, dot. All kinds of typos. Oh, I should put subscript, sorry. All right, so we've been dealing with differential equations with constant coefficients, right? So we've found a way to solve for those differential equations by looking at their auxiliary equations and then solving for those and then just putting them as powers of E. We dealt with multiplicities, we dealt with complex numbers. So we're all good with the homogeneous differential equations. So now let's take a look at what happens if you have a non-homogeneous differential equation, which is to say that the right-hand side is equal to something that's other than 0. So what are we going to do for that? Well, our first step in dealing with this is hope that our right-hand side is a simple function. And when it gets complicated, then we'll deal with that as a different problem. But for right now, let's restrict our right-hand sides to simple polynomials. That's p of x, any polynomial. Exponential functions, e to the x, or e to the 2x, e to the k times x, or a combination of sine and cosine. So that's what we're going to do. What we're doing here is we're solving for a particular solution. We want to find a particular solution. If you don't remember what that was, the definition of a particular solution is a solution of a function that would satisfy this non-homogeneous differential equation. So we're going to try to find out what that solution is going to look like. So let's take a simple example. What was the easy example that we did last time? So let's take this example where we have this thing, and let's let it equal to either a polynomial or an exponential function. So those are the first two types of easy types of problems to deal with. So example, what was it? Y double prime minus 10y prime plus 25. minus 10y prime plus 25y. And now let's let it equal to something. Let's let it equal to e to the x. Okay, so the question here is that what is your particular solution? And the particular solution is usually denoted by y sub p. Okay? So just like what we've done before, we're going to assume that this particular solution is going to be something that's related to that right-hand side, right? So what we're going to do is assume that y sub p is equal to something that looks like e to the x. Yeah?
So when you have a homogeneous differential equation of n plus 1 degrees of freedom,
Yes.
choosing it. But as soon as you have a non-homogeneous one, then you drop down to 1 degree of freedom?
No, the general solution is still going to be in n degrees of freedom. And this right now is just a particular solution, but the general solution will need that information from the homogeneous part. And then we'll tack it all up together. That's the superposition principle. All right. So let's see how this is going to fly here. I'm going to assume that this is my solution. Now I threw in this extra a here. This extra a is called an undetermined coefficient. This whole process is called the process of undetermined coefficient. Okay, so I have 2 minutes. Let's see. The derivative of this, y sub p prime is equal to a e to the x. Y sub p double prime is equal to a e to the x. So put them all in. A e to the x minus 10 a e to the x plus 25 a e to the x is equal to e to the x, right? Did I make a mistake? A is a constant, yeah. So let's factor out an e to the x from the left-hand side and realize that the coefficient of e to the x is 1. And so this whole thing has to equal to 1. So a minus 10a plus 25 is equal to 1. So what's this equal to? 9, negative 9? Negative 24. Right? So here, your particular solution, y sub p, is equal to 8 over 3 times e to the x. Yeah. Because your solution, your particular solution, should look a lot like the right-hand side of your non-homogeneous differential equation. Patrick. Oh, yeah. That's still, I think it still turned out okay, right? Oh, then that's not the right answer, huh? So what should it be? 1 over 16? All right, sorry, this is 1 over 16. All right, we'll come back to this example next time. Actually, you know what? I'm going to finish this example in the video, and I'll expect you to just look at it, and then you guys can... All right, see you guys next time. Oh, a week from now. No Thursday class.